Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. We've seen that complex conjugation is a symmetry of the field of complex numbers, which allows us to study the real numbers. Now, we want to, of course, use this idea to study other fields as well. And to do so, then, we need to be able to construct lots of field isomorphisms. And that's the objective of this video today. So for our basic construction of field isomorphisms, let F denote some sort of field. And what we're going to do is we're going to consider a simple algebraic extension of this field F. Let's call it K. So if it's a simple extension, that means that we can write it in the form F of alpha. That is, it's generated by a single element alpha inside K. So every element inside K is just some sort of polynomial in alpha whose coefficients are inside F. Okay, so that's what simple means. And we want it to be algebraic as well, which means that alpha is a zero of some polynomial with coefficients in F. And in fact, of course, we can pick that polynomial to be minimal in degree and let that minimal polynomial be P of X. So that's a polynomial with coefficients in F. Okay, so in this case, we have a certain description of this K, okay, which gives us a field isomorphism. It's a field isomorphism as follows. Okay, you can make it isomorphic to, firstly, we start with a polynomial ring, F of X, and we're going to take the quotient ring by the ideal generated by P of X. So remember, this is a minimal polynomial, so it's going to be irreducible. And since it's irreducible, that means it's actually a maximal ideal inside this principal ideal domain. So being a maximal ideal, when you quotient it out, you get a field. So there's an isomorphism of fields like that. And you could say a little bit more. In fact, it's an F-linear field isomorphism. Okay, so this F of X, this is a vector space over F. And since this ideal is an ideal, this is also a vector space over F. Well, what about this K? So this K here is also a vector space over F. So remember that firstly, it contains a copy of F. Okay, it's also an abelian group, so it has the additive structure of vector space. And to get scalar multiplication by elements inside here, we just restrict the ring multiplication to this subset, or this subfield F. Okay, so let's see what this F-linear field isomorphism is. It's quite easy to describe. So firstly, if we take an element inside here, it's some coset of some sort of polynomial, F of X. And what does it get mapped to? So this is a polynomial with coefficients inside F. So what we can do is we can just substitute in alpha for our indeterminate X. That's F of alpha. So one way to think of it, for example, if your polynomial is just X itself, okay, and you look at that coset, what does it get mapped to? You just substitute for X alpha. So this is a F-linear field isomorphism, which essentially, well, on F, it's going to fix F. Okay, in fact, that's the equivalent way to think about F-linearity here. And for X, you just need to really say what happens to this X, which generates this ring, okay, over F, is that it goes to alpha. Okay, so let's just see why this is true. Hopefully you've seen this before. So it's a nice application of the first isomorphism theorem for rings, and it uses the following surjective ring homomorphism. So it goes from the polynomial ring Fx to K, and it's basically this evaluation homomorphism. So let's just write it out more explicitly what that does. So if you have a polynomial inside here, so say with coefficients Fi inside this field F, and it's a polynomial like that, what does it get mapped to? It gets mapped to, you basically substitute every time you see the indeterminate X you put in alpha. Okay, so if you look at this, remember K was assumed to be of this form. So this is surjective, okay. This is going to be a field, okay, and it's going to be the set of all polynomials in alpha with coefficients inside your field F. This is going to be surjective. It's quite easy to see that this is a ring homomorphism. You can write this out using the ring multiplication for polynomial rings and using the distributive law over this side. Okay, so you have a ring homomorphism, and then you just have to check that the kernel is indeed this P of x. And the point is that, well, what happens when you put in P of x? So this is just a way of expressing this map here. Well, remember, P of alpha is 0 because P is the minimal polynomial of alpha. So alpha is a root of P of x, so P of x goes to 0. Okay, so P of x is in the ideal, and so is the whole of the ideal generated by P of x. And can the kernel be any bigger than that? Well, this is a maximal ideal, so it can't be any bigger. Okay, so that tells you that that's indeed an isomorphism. And it's quite easy to check that this is actually an F-linear field isomorphism. If you multiply by a scalar f, it just multiplies all these coefficients by that scalar inside f, and that maps to the corresponding thing over here. So it's F-linear like that. Of course, this is additive. Okay, so this is an abstract proposition, hopefully one that you've seen in your field theory courses before. But let's see how it's useful for constructing field isomorphisms that are interesting for us, okay? So things which are like the complex conjugation. Okay, so what we'll do here is we'll look at some subfields of complex numbers. So we'll let zeta equal this primitive cube root of the identity, okay, e to the 2 pi I on 3. And what we'll start off with is q adjoint the cube root of 2. So this is a simple algebraic extension. Okay, cube root of 2. What's the minimal polynomial of this over q? Okay, so it's certainly a root of x cubed minus 2, and this is the smallest or the smallest degree polynomial for which this has this as a root. So this proposition straight away tells you that this is isomorphic to qx modulo the ideal generated by x cubed minus 2. Well, very well and good, but these aren't the types of things that we're interested in. They're not the fields that we want to play around with. So what do we do instead? Okay, well, we noted that x cubed minus 2 is also a root of, also has 2 other roots, okay? So this is also the minimal polynomial over q of cube root of 2 zeta. Okay, if you multiply this by primitive cube root of infinity, you get another 0 of this. So you also have this isomorphism here. So now we get a field isomorphism from q adjoint cube root of 2 to q adjoint cube root of 2 times zeta. And what this does is it will send this cube root of 2. Remember here, this alpha here gets mapped to the x. This corresponds to the ideal or the coset of this ideal given by x. And x here, on the other hand, gets mapped to what? It gets mapped to cube root of 2 zeta. So there is now a field isomorphism, a q-linear field isomorphism from q adjoint cube root of 2 to q adjoint cube root of 2 zeta, which sends cube root of 2 to cube root of 2 zeta. Now, of course, the things that we're interested in, if we want a symmetry, is we want an automorphism. So here we go from one field to a different field. So how do we get a field automorphism? Okay, so we can apply the following trick that I will illustrate in an example, okay, which is quite stereotypical. Okay, so what we're going to do is, well, these differ. So what we're going to do is, well, since we have a cube root 2 zeta here, let's throw that into here. Okay, so let's have a look at this. So we're going to start with this field here. Okay. And we're going to throw in this cube root 2 zeta. So let's look at the minimal polynomial of cube root 2 zeta, not over q, which would be this one here, but over this bigger field. Okay, so we're going to do that. Okay, so firstly, how do we do that? So firstly, remember, the minimal polynomial of cube root 2 zeta over q is x cubed minus 2. Okay, so that's what that is. But now you're going to look at the minimal polynomial over q adjoint cube root of 2, and this contains a root of this. Okay, so what you need to do, in fact, to find that, so note that this is of course not inside here, so this minimal polynomial can't be linear, it's got to be at least quadratic, and it also doesn't have the factor x minus cube root of 2. X minus cube root of 2. So what you do is you just factor out from this cubic x minus cube root of 2, and that's going to be your answer. So that's quite easy to do because you can use the difference of cubes results to find out what that is. Okay, so that's going to be x squared plus, and then you have cube root of 2 x plus cube root of 2 squared, which is cube root of 4. Okay, so it's quite easy to see if you multiply this by this here, okay, that you'll get x cubed minus 2. Okay, and that's your answer. So here is the minimal polynomial of cube root of 2 zeta over this string here. And you can see the coefficients do lie inside this field here, this bigger field, okay? And it's now quadratic. Okay, so that's good. So we've got a situation where we have a minimal polynomial. We've calculated this minimal polynomial of something over this field. And what we're going to do now is we're just going to apply this field isomorphism to what's happening here. So more precisely, what's going on. So firstly, if you have any field isomorphism, okay, or any ring homomorphism, in fact, it induces a ring homomorphism on the polynomial rings. So what we can do is we can apply phi to each of the coefficients here, and that's a ring homomorphism. And that ring homomorphism I'll denote by phi bracket x like that. And I'll apply that to q of x. Okay, so we just apply this field isomorphism to all the coefficients. So the coefficient 1 here gets sent to 1, so you get x squared. The coefficient cube root of 2 here gets sent to cube root of 2, so that's cube root of 2 zeta x. And the coefficient cube root of 4, which is cube root of 2 squared, gets sent to, well, cube root of 2 gets sent to this. So the square of this will get sent to the square of this, so that's cube root of 4 zeta squared. Cube root of 4 zeta squared. Okay, so you've just applied this field isomorphism, and you get a new polynomial. And of course, this is a polynomial. Where is the polynomial? Okay, because you applied this phi to the coefficients now lie inside here. So the coefficients lie inside here, so it's a polynomial over there. Okay, so let's have a look at that, and let's factorize this and see what are the roots inside the complex numbers. And it's quite easy to see what the roots are inside the complex numbers, and you can check this yourself. So one of the roots is cube root of 2, and the other root is cube root of 2 zeta squared. Okay, so let's just trickily check to see that this looks correct. Okay, so if you look at the x squared term, you get x times x is x squared. If you look at the constant term, it's cube root of 2 times cube root of 2 here times zeta squared. That's cube root of 4 times that zeta squared. And the minus minus gives you a plus. Okay, and the final thing is that what's the coefficient of x? Okay, you have a negative cube root of 2 and a negative cube root of 2 zeta squared. Okay, so here's the cube root of 2, and what's minus 1 minus zeta squared? That's plus zeta. So remember, the sum of the 3 cube roots of unity is 0. So minus 1 minus zeta squared is plus zeta. Okay, so we factorize that. So what do we see from this calculation here? So we see from this calculation is that firstly you have this polynomial here that's inside cube root 2 zeta, and it has this root cube root of 2. So the minimal polynomial of cube root of 2, okay, over this q adjoint cube root of 2 zeta is precisely this one here. Okay. And how do we know it's the minimal polynomial? Firstly, it is a root of this polynomial. And secondly, this is minimal in the sense that, well, the minimal polynomial can't be any smaller. If it was smaller, it would have to be linear, so it would have to be x minus cube root 2. And that would suggest that this is inside this field, but this is clearly not inside this field. Okay, so they're different fields. Okay, and now we're going to construct our field isomorphism by using this proposition several times and this one extra trick of applying the field isomorphism that we had before to coefficients. Okay, so let's see how that works. Okay, so let's use this first part here to see what's going on. So here we have a minimal polynomial. So what we can do is we can look at the simple extension where we throw into this q adjoint cube root of 2, q adjoint cube root of 2, this cube root of 2 zeta, cube root of 2 zeta. And this proposition says that we can find a isomorphism of that with some quotient of some polynomial ring. What is that? So it's a polynomial ring of q adjoint cube root of 2 zeta x. And you have to factor out by the minimal polynomial of this cube root of 2 zeta over this coefficient field. And that was this q of x that I wrote here. Okay, this x squared plus cube root of 2x plus cube root of 4. So here we have a field isomorphism. That's all very well and good. And now what do we do? Well, what we're going to do now is that we're going to apply a field isomorphism onto this polynomial ring, and it'll map over to this one here. So you're going to apply phi to the coefficients. So it sends q adjoint cube root of 2 to q adjoint cube root of 2 zeta, and we get the corresponding polynomial ring here. And what does the ideal map to? The ideal generated by q of x gets mapped to the ideal generated by whatever phi of x sends this q of x to. And we computed that just right up here. Okay, so we computed that to be this polynomial here, x squared plus cube root of 2 zeta x plus cube root of 4 zeta squared. And now what do? We recognize that this is actually the minimal polynomial of cube root of 2 over q adjoint cube root of 2 zeta. So using this proposition for once more, okay, we find that there's an isomorphism like this. Okay, and now if you have 3 q linear field isomorphisms, you can compose them and you get another q linear field isomorphism. And what it does, well, here, just to see what's going on here, okay, if we trace what happens, cube root of 2 goes to the cube root of 2 here, the constant polynomial, or the coset containing that. You apply phi to the coefficient, so this gets sent to cube root of 2 zeta. So that goes to cube root of 2, cube root of 2 zeta. There's the cube root of 2 zeta. Okay, and you can also see that cube root of 2 zeta, where does that get sent to? Well, under this map here, this gets sent to the x. Okay, that's what happens here, because that's the element that you're joined. The alpha corresponds to the x. X, well, you apply now phi to the coefficient, so the coefficient is 1, so this sends to x. What does x correspond to over here? Well, now that's the thing that you're joined, which is cube root of 2. So basically, it's just going to swap your cube root of 2 with your cube root of 2 zeta. Okay, and now finally we get something which is a field isomorphism from the same field, q adjoint cube root of 2, cube root of 2 zeta. Okay, there's a field isomorphism, a q linear field isomorphism from this to itself. Okay, so let me just sum up the basic principles that are outlined in this simple example. Okay, and it gives you what I've called automorphisms of splitting fields. So let me define for you this very important concept of a splitting field. Okay, a splitting field for, suppose you have some field f and you have a polynomial p of x. So what is a splitting field for this p of x over f of x? It's going to be some sort of field extension k in which this firstly splits completely. Okay, and so this k contains a complete set of roots of p of x, and furthermore it's generated by that complete set of roots. Okay, so I'll give you a little example in a moment. So what do I mean by a complete set of roots? So I mean by a complete set of roots is that, well, if you have a root of this p of x in some field, that means that you can factor it and pull out a linear factor corresponding to that root. So p of x, if you think of it as a polynomial in kx, it factors completely into linear factors. And if you look at all those linear factors and look at the corresponding roots, k is actually generated by those roots. Okay, so that's what it means to be a splitting field for p of x. And in this case, we'll just say that this k over f is a splitting field or is normal. So if there exists some sort of a polynomial like that for which this holds, then we say it's a splitting field or it's normal. Okay, so let's just look at a simple example. Let's have a look at x cubed minus 2. That's a polynomial over the rationals cube. And what are the three roots? The three roots are cube root of 2, at least inside the complex numbers, cube root of 2, cube root of 2 zeta, and cube root of 2 zeta squared. So the splitting field for x cubed minus 2 over q, or one of them, the one that sits inside the complex numbers is just Q adjoin these three things. Of course, you can write this in lots of different ways. For example, I could also write this as Q adjoin cube root of 2 and zeta, okay, just to see that they're equal. Hopefully this is an exercise you know how to do. So certainly each of these three roots is contained inside here. You can get them by multiplying this cube root of 2 by appropriate power of this zeta. And also to see that, so that tells you that this right-hand side is contained in the left-hand side. And to show the converse, that the left-hand side is contained in the sides of the right-hand side, well, cube root of 2 is already here. And also zeta is inside here because it's a quotient of this one by this one. Okay, so it may not look like it's generated by roots of a single polynomial, okay, but in this case it is. Okay, so there you have a splitting field. And what proposition sort of sums up how we can construct automorphisms? Okay, so suppose now you have an irreducible p of x, a polynomial with coefficients in f. Okay, and k is a splitting field for that polynomial. Okay, so of course we want to construct non-trivial automorphisms. Okay, so what we're going to do is we're going to pick two roots alpha beta inside k of p of x. Then actually what this basic argument shows is that you can always construct an F linear field automorphism of this splitting field, phi from k to k, and it's going to send alpha to beta. You can always do that. Okay, so the way you'll do that is you use this part of the trick first, okay, and then you have to do some sort of inductive step using this type of argument to get the automorphism. So the initial field isomorphism will send you from F adjoin alpha to F adjoin beta, and then what you do is that you complete that somehow using this part of the argument to get you a automorphism from k to k. Okay, so this is really nice. So this allows us to construct field automorphisms, and this will play the role of something like a complex conjugation in Galois theory. Okay, let me just finish off with a couple of remarks which are good to note. Okay, so firstly, F linearity. What does that really correspond to? Okay, so another way to state F linearity here is that, here, this K, remember, is a field extension of F, so it contains F. And what it means is that what does it do to F, this phi? It just sends gamma to gamma for every gamma inside F. So why is that true? So firstly, of course, field isomorphisms have to send 1 to 1, and if it's going to be F linear, so it preserves scalar multiplication by gamma, that means that it sends phi of gamma. You can pull the gamma out, so it sends phi of gamma to gamma times phi of 1, so that's gamma times 1, which is gamma. And it's quite easy to show the converse, that if this holds, then of course, in fact, since this is a ring, it preserves ring multiplication, that this is an F linear map. Okay, so that's the converse. So the other thing that's kind of nice about this example is that, well, what types of things have we done here? Here we've swapped two of the roots of x cubed minus 2. And in fact, the original way that Galois thought about the Galois group was in terms of swapping roots. Okay, so it turns out that in this particular example, it's rather nice that given any permutation of the roots cube root 2 zeta, and cube root 2 zeta squared, okay, any permutation, you can lift that to an automorphism of this field. Okay, so we've seen the example where we stopped cube root of 2 and cube root of 2 zeta, but of course all the three roots are fairly symmetric. Okay, we could play this game with any two of them and swap them, and if you can do any two swaps, of course you can combine them to get you any permutation that you like. I hope you enjoyed this adventure in pure mathematics.